Picture a piece of paper. Nothing dramatic, nothing rare, just a simple line of numbers and letters, the kind of thing that has been written, erased, rewritten, and sighed over in classrooms for generations. X 5, L's 12. It is almost too ordinary to look at twice. Millions of students have copied a line just like it into a notebook, half asleep, waiting for the bell. It doesn't look like the beginning of a story. It looks like homework. But sit with it for a moment. That small collection of symbols, that letter standing in for something unknown, that equal sign holding two sides of a sentence in balance, carries something most of us never think about. It carries a word, and that word, algebra, has a history that reaches back more than 1,000 years to a scholar working in the intellectual world of 9th century Baghdad. His name was Muhammad ibn Musa Al-Khwarizmi. You may never have heard of him. Most people haven't. And yet, in a strange and quiet way, his name is with us constantly, folded into a word we use without noticing, the way a foundation is folded into a building. Every time someone says algebra, they are, without knowing it, saying something that traces back to a book he wrote. And that is only the first half of the story. Because hidden inside his own name, inside the way it was carried out of the Arabic-speaking world and into Latin, and from Latin into the languages of Europe, is another word, a word that now sits at the center of modern life: algorithm. Today, algorithms quietly shape an enormous amount of what surrounds us. They decide what appears on a screen. They route a delivery. They price a plane ticket. They recommend a song. They sit somewhere inside almost every piece of software we touch, humming along in the background of ordinary days. So here is the question this documentary sits with tonight. How did the name of a mathematician from more than 1,000 years ago end up embedded in the language of the digital age? That is the mystery we're going to walk through slowly. Not because it needs to be rushed, but because it deserves the opposite. Let it unfold the way these things actually happened. Gradually, across centuries, across languages, across civilizations, passing an idea from one set of hands to another. Why this story, and why now? When the research for this documentary began, something became noticeable fairly quickly. Explanations of algebra are everywhere. Videos about algorithms are everywhere. That word has practically become a subject of its own on the internet, tied to everything from social media to artificial intelligence. But it was surprisingly difficult to find something that simply slowed down and asked the more basic question underneath all of it. Who was the man behind these words? What did he actually write? What did he actually contribute, and what did later generations add to his ideas over time? And how did his work travel, physically and linguistically, from a walled city on the Tigris into the mathematics and technology that now sits in your pocket? Perhaps that gap is exactly why this story is worth telling slowly and worth telling carefully. This is Sleep with Islam, a channel built around the idea that certain stories from Muslim history deserve to be heard at a quieter pace than the internet usually allows. Stories of scholars, physicians, astronomers, engineers, and thinkers whose work quietly became part of a much larger human inheritance. Not to boast about the past, just to understand it, to see how knowledge actually moves, person to person, book to book, century to century. Before we travel back, it's worth sitting for just a moment with how close this story actually is to your own life, even if it doesn't feel that way at first. If you've ever solved an equation in school, if you've ever used a calculator or followed a formula in a spreadsheet. If you've ever searched for something online, unlocked a smartphone, watched a streaming service quietly recommend what to watch next, used GPS to find your way somewhere unfamiliar, sent money to someone through an app, or written even a single line of computer code, you are living inside a world built, layer upon layer, on systematic mathematical procedures, not because one person built all of it, but because a very long chain of people across many centuries and many civilizations kept refining the idea that a problem could be solved through a clear, repeatable method rather than guesswork. To be careful and honest about this from the very start, the man at the center of tonight's story did not build any of that world directly. He did not invent computers, software, or the internet, and it would badly misrepresent his life to suggest otherwise. What he did was help develop mathematical ideas and systematic procedures that became part of a much longer intellectual history. A history with many contributors across many centuries that eventually led toward the digital world surrounding you right now. He is one link in that chain, an important one, but a link, not the whole chain. If that kind of quiet journey through history is something you'd like to return to, you're welcome to subscribe. But there's nowhere you need to be right now. Let the equation rest on the page for a moment. Let's go back to Baghdad. Chapter 1. What exactly is algebra? Before we meet the man, it's worth sitting with the question his most famous book answers. What is algebra really? At its simplest, algebra is a way of talking about the unknown. Arithmetic deals with numbers you already have, 3 apples plus 4 apples. Algebra deals with a number you don't have yet, one you are trying to find, and gives you a systematic way to find it. Instead of guessing, you build a sentence, an equation that describes a relationship, and then you follow a set of steps that peels the unknown quantity out into the open. That might sound abstract, but it solves something extremely concrete. If a piece of land has a certain area and one side is unknown, algebra gives a path to the answer. If money is being divided among heirs according to a set of rules, algebra gives a path to the answer. It is, in a sense, a machine for solving problems that would otherwise require trial and error. The English word for this entire branch of mathematics, algebra, comes almost unchanged from Arabic. It is drawn from the title of a book written in 9th century Baghdad. Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala. In English, something close to the compendious book on calculation by completion and balancing. 2 words inside that title matter enormously, and we'll return to them properly a little later. Al-Jabr meaning something like completion or restoration, and al-Muqabala meaning balancing. Together they describe 2 operations, 2 moves you can make on an equation to simplify it until the unknown quantity stands alone. It is not too far off to say that this book gave algebra both its name and, in a real sense, its first systematic shape. It's also worth being clear before we go any further about what algebra was not in its earliest form. It was not yet the symbolic language modern students recognize, with its neat X's and plus signs and equal signs lined up in a row. Al-Khwarizmi wrote entirely in prose, full sentences describing quantities and operations in words with no mathematical symbols at all. The tidy symbolic notation familiar today developed gradually over the centuries following Al-Khwarizmi through the work of many later mathematicians in both the Islamic world and Europe. What Al-Khwarizmi contributed wasn't the notation. It was the underlying method, the idea that equations could be sorted into a small number of general types, each solvable by a repeatable procedure, regardless of what specific numbers happen to be involved. Which raises the obvious question, why would anyone in 9th century Baghdad need to write such a book in the first place? To answer that, we need to understand the city that produced it. Chapter 2. Baghdad. Baghdad, in the early 9th century, was one of the great cities of the world. It had been founded a few decades earlier, in 762, by the Abbasid Caliph Al-Mansur, built in a roughly circular plan on the banks of the Tigris River. By the time our story begins, it was the capital of an empire that stretched from the western edge of North Africa to the borders of India. An empire governed from this single city and drawing scholars, merchants, and manuscripts toward it from every direction that empire touched. The caliph who set much of this in motion, historically speaking, was Harun al-Rashid, who came to power in 786. Around the same time, historians estimate that Al-Khwarizmi was born. Harun ruled from Baghdad and, in the words of historians who study the period, worked to bring learning and culture into his court in ways that had not been firmly established there before. After his death in 809, a war broke out between his two sons, Al-Amin and Al-Mamun. Al-Mamun won that struggle in 813 and took the throne. It was Al-Mamun who gave the intellectual life of Baghdad its most famous institution, an academy generally known as the House of Wisdom, or Bait al-Hikmah. Here, scholars worked to translate Greek philosophical and scientific texts into Arabic. Al-Mamun is also said to have built a major library of manuscripts, by some accounts the most significant library assembled since the ancient Library of Alexandria, and to have established observatories where astronomers could carry earlier traditions of sky-watching forward with new precision. It's worth pausing here because it's tempting, and this documentary wants to resist the temptation, to picture the House of Wisdom as something like a modern university campus with lecture halls and a tidy administrative structure. The reality, according to historians, is less clearly defined than that image suggests. What we can say with more confidence is that Baghdad, in this period, had become a genuine center of gravity for scholarship, a place where Greek geometry, Persian court traditions, Indian astronomy, and the emerging concerns of an Islamic legal and administrative state were all, in different ways, in the room together. This is the atmosphere that historians describe when discussing the period. Mathematics in Baghdad around the turn of the 9th century was shaped by contact with Hindu mathematical traditions arriving from the East, alongside a steady stream of Greek scientific works being translated from manuscripts gathered from Byzantium and elsewhere. Knowledge, in other words, was already in motion long before our central figure appears in the story. He did not begin this movement. He stepped into the middle of it. Picture for a moment what that city might have felt like. Baghdad had been laid out decades earlier in a roughly circular plan, ringed by walls, with the Caliph's palace and the great mosque set at its center. A design meant to project order onto a rapidly growing capital. Beyond the palace walls, the city would have been full of the ordinary noise of a major trading hub. Markets selling goods carried in along routes stretching from China to the Mediterranean. Canals threading off the Tigris to irrigate surrounding farmland, scribes and copyists at work reproducing manuscripts by hand, one page at a time, for a growing class of scholars and officials who needed them. Al-Khwarizmi was not the only scholar drawing on this atmosphere. His colleagues at the House of Wisdom included the three brothers known collectively as the Banu Musa, who worked alongside him on geometry and astronomy and later became noted scholars and patrons of learning in their own right. Other translators of the period, such as Al-Hajjaj ibn Yusuf, had rendered Euclid's Elements into Arabic during the years Al-Khwarizmi was still young. A text that, as we'll see, may have shaped the geometric reasoning behind Al-Khwarizmi's own Algebra. Slightly later in the century, scholars like the physician and translator Hunayn ibn Ishaq would carry the same translation movement forward into medicine and philosophy. None of these figures worked in isolation. They were colleagues, sometimes collaborators, occasionally rivals, all drawing from and contributing to the same expanding pool of translated and original knowledge circulating through the city. And it was in this environment, a city of translators, astronomers, administrators, and mathematicians, all working under the patronage of a caliph interested in learning, that Muhammad ibn Musa al-Khwarizmi did his work. This period is sometimes referred to in popular writing as part of the Islamic Golden Age, a phrase worth pausing on briefly before moving forward, because it's easy to let a label like that flatten something more complicated than it suggests. The phrase is generally used to describe a broad stretch of centuries across a vast and varied territory, during which particular cities and courts, Baghdad prominent among them, saw notable concentrations of scientific, mathematical, and philosophical activity, often supported by rulers with a direct interest in learning. It does not mean that every part of the Muslim world was equally prosperous or equally invested in scholarship at every point during this period, any more than a Golden Age label applied to any other civilization would mean uniform flourishing everywhere at once. Nor should it suggest, by contrast, that other regions of the world, including Europe in this same period, were somehow uniformly without learning or scholarship of their own. History rarely divides itself so neatly. What can be said with more confidence, specifically and locally, is that Baghdad, under al-Mamun's patronage in the particular decades when Al-Khwarizmi was active, was a genuine and unusually concentrated center of mathematical and scientific work. And it's within that specific, bounded reality, rather than any sweeping civilizational claim, that this documentary wants to stay grounded. Chapter 3. Who was Al-Khwarizmi? Here the story does something a little unusual for a documentary. It has to slow down and admit what it doesn't know. We can say with reasonable confidence, based on the surviving evidence, that Muhammad ibn Musa al-Khwarizmi lived from around 780 to around 850. Historians who have studied his life closely, figures like J. Toomer and Roshdi Rashid, describe how thin the actual record is. As one major reference source on the history of mathematics puts it plainly, we know very few details of his life, and that thinness of evidence has over the years tempted some writers into filling the gaps with guesswork that isn't well supported. Even his name carries an open question. Al-Khwarizmi suggests a connection to Khwarazm, a region south of the Aral Sea in Central Asia, in what is now largely Uzbekistan and Turkmenistan. But the 9th century historian Al-Tabari also referred to him by a second name, Al-Kutrabuli, which points instead to Kutrabul, a district near Baghdad itself, between the Tigris and Euphrates. Scholars disagree about exactly what this means. It may indicate that his family, rather than he himself, originally came from Khwarazm, with Al-Khwarizmi himself having been born and raised much closer to Baghdad. Different historians have read the surviving Arabic sources differently, and at least one, Rashid, has argued that a small error in how an old manuscript was copied, a single missing word, led later writers to draw conclusions about Al-Tabari's report that the original text may not actually support. We are, in other words, dealing with a life partly reconstructed from a handful of medieval sentences that don't always agree with each other, and that later historians have sometimes stretched further than the evidence really allows. There's a second epithet attached to his name in the medieval sources that adds another small layer of uncertainty rather than resolving it. The historian Al-Tabari also referred to him in the same passage using the term al-Majusi, a word generally used to indicate an adherent of the older Zoroastrian religion of pre-Islamic Persia. Taken at face value, this might suggest Al-Khwarizmi himself, or at least his family background, had roots in Zoroastrianism before converting to Islam, something that would still have been entirely plausible for a family of Iranian origin at that point in history. But the devout religious preface Al-Khwarizmi wrote to open his own algebra treatise makes clear that he himself was, by the time he wrote it, a practicing and orthodox Muslim. So the most that can reasonably be drawn from this second epithet, historians suggest, is that his more distant ancestors, or perhaps Al-Khwarizmi himself in an early period of his life, may have had Zoroastrian roots, without that telling us very much more about the man who later wrote the book that made him famous. It's worth being honest about why these small details matter, even though they can feel like minor scholarly hair-splitting. They matter because they're a useful lesson in how careful real historical work has to be. A single ambiguous word in a 9th century Arabic manuscript, copied and recopied by hand over centuries, can spawn genuinely different interpretations of a person's origin, ancestry, and even religious background. Interpretations that responsible historians hold with appropriate uncertainty rather than presenting as settled fact. This documentary tries to hold that same uncertainty rather than resolve it artificially for the sake of a cleaner story. What is more solid is his professional life. Al-Khwarizmi worked in Baghdad, associated with the scholarly circle gathered around the House of Wisdom, alongside colleagues such as the Banu Musa brothers. Their work there involved translating Greek scientific manuscripts and writing original treatises on algebra, geometry, and astronomy. Al-Khwarizmi worked under the patronage of the Caliph Al-Mamun and dedicated 2 of his most significant books directly to him: his treatise on algebra and his treatise on astronomy. Beyond that, his childhood, his personal relationships, what he looked like, how he spoke, what kind of temperament he had, the historical record goes quiet. There are no surviving letters describing his personality, no contemporary portraits, no anecdotes about arguments in a lecture hall or breakthroughs achieved in a single dramatic evening. What survives is almost entirely his written work, and the echoes of that work in later scholars who read, copied, translated, and built upon it. That silence is worth sitting with rather than filling in. It tells us something true about how history actually preserves people. Sometimes it keeps the book and loses the man. We will meet Al-Khwarizmi almost entirely through what he wrote, which, as it turns out, is more than enough to understand why he mattered. Beyond his major works on algebra, arithmetic, astronomy, and geography, the surviving record also credits Al-Khwarizmi with a handful of smaller treatises, 2 separate works on the astrolabe, an instrument used for astronomical observation and timekeeping, a treatise on the sundial, a work addressing the Jewish calendar, whose lunar-solar calculations required careful mathematical handling, and, more unusually to modern eyes, a political history that included horoscopes cast for prominent figures of the period. A reminder that astronomy and astrology were not always cleanly separated disciplines in the 9th century the way they are today. None of these minor works survive in the kind of detail that would let us reconstruct Al-Khwarizmi's daily working life, but together they sketch a picture of a scholar whose interests ranged fluidly across mathematics, the instruments used to observe the sky, and the practical, calendrical needs of the empire he served. Chapter 4. The book that gave us algebra. Al-Khwarizmi's algebra treatise survives in a translation by the 19th century scholar Frederick Rosen, and in it we can hear Al-Khwarizmi describing, in his own words, why he wrote the book. He says he intended to teach what was most useful and necessary in calculation, the kind of mathematics people constantly needed for matters of inheritance, legacies, division of property, lawsuits, trade, the measuring of land, the digging of canals, and geometrical problems of various kinds. That list is worth pausing on because it tells you something important. This was never meant to be an abstract exercise for its own sake. It was a practical handbook aimed at solving the kinds of real disputes and calculations that came up constantly in the administrative and commercial life of the Abbasid Empire. How to divide an inheritance fairly according to Islamic law, how to measure a plot of land, how to work out a fair trade. Only the first portion of the book is what we would recognize today as algebra in the strict sense. Al-Khwarizmi opens by explaining the natural numbers in terms so basic they can seem almost quaint to modern readers, walking through step by step how numbers build from units up through tens and hundreds. It reads slowly to us now, but it reflects a real effort to build understanding from the ground up rather than assume it. From there, he introduces the heart of the book: solving equations. In his system, there were three basic kinds of quantities: a unit, a plain number, a root, what we'd now call x, and a square, what we'd now call x2. Every equation he deals with can be built from these three ingredients, reduced down to one of 6 standard forms. For example, squares and roots equal to numbers, which in modern notation might read x2 plus 10 to x equals 39. To get an equation into one of these standard forms, Al-Khwarizmi used 2 operations, and these 2 operations are the actual origin of the word algebra. The first was Algebra, restoration or completion, the process of removing negative terms from one side of an equation by adding them to both sides. The second was Al-Muqabala, balancing, the process of cancelling out matching positive terms that appear on both sides of an equation. Together, these 2 moves are, in essence, the earliest systematic ancestor of what a modern algebra student does today when they move a term across the equal sign. He then shows, worked example by worked example, how to solve each of his 6 standard equation types, sometimes using purely arithmetic reasoning and sometimes using geometry. For an equation like x2 plus 10x equals 39, he walks through what is essentially the method known today as completing the square, a technique still taught in classrooms right now, nearly 12 centuries later, that traces directly back to the reasoning in this book. He supports the arithmetic explanation with a geometric picture, a square of unknown side length with rectangles attached to represent the added terms, until the whole figure can be measured and the unknown side found. Historians have long debated exactly where Al-Khwarizmi's geometric reasoning came from, whether he was directly familiar with Euclid's Elements, which had recently been translated into Arabic by a colleague of his at the House of Wisdom, or whether he was drawing more on older Near Eastern surveying traditions. The honest answer, based on the surviving evidence, is that scholars are divided. Some see clear traces of Euclidean geometry in his method. Others argue his approach looks quite different from Euclid's formal style, with no definitions, axioms, or the kind of step-by-step logical proof structure Euclid used. What seems most likely, in the judgment of many historians, is that Al-Khwarizmi was working within a broader geometric tradition, one that may have included Greek but also Hebrew and older Near Eastern surveying methods, rather than following any single source directly. One historian, Karen Parshall, has noted that Al-Khwarizmi's treatment of practical geometry follows the much older Hebrew surveying text known as the Mishnat Hamiddot, closely enough to suggest a shared line of descent stretching back through Semitic mathematical traditions, quite apart from the Greek geometry of Euclid. It's worth walking through Al-Khwarizmi's method a little more closely, because the reasoning itself is genuinely elegant, even stripped of modern notation. Take the equation that, in modern symbols, would read x2 plus 10x equals 39. Al-Khwarizmi describes it in words. A square, together with 10 of its roots, is equal to 39 units. His instruction is to take half of the number of roots, half of 10, which is 5, and multiply that by itself, giving 25. Add that to 39, giving 64. Take the square root of 64, which is 8, and subtract the 5 you started with. What remains, 3, is the unknown root, meaning the square itself is 9. Run that same reasoning through geometry, and it becomes visible rather than just calculable. Picture a square with an unknown side length. That square represents x2. To represent the added 10x, attach 4 narrow rectangles to its 4 sides, each with a length equal to the unknown side and a width of 2.5. The combined shape, square plus 4 rectangles, has an area equal to 39. Now fill in the 4 small corner squares left empty by this arrangement, each with an area of 2.5 times 2.5 or 6.25, and a new, larger, complete square emerges with a total area of 64. Since the area of a square is the side length multiplied by itself, and 64 is 8 multiplied by 8, the side of this larger square must be 8. But that side is also equal to the unknown length, plus 2.5 on one end, plus 2.5 on the other, so the unknown length itself must be 3. 2 completely different roots, pure calculation, and a geometric picture built from squares and rectangles arrive at exactly the same answer. That doubling of method, calculation confirmed by geometry, is part of what later readers found so persuasive about Al-Khwarizmi's approach. It wasn't simply a set of rules to memorize, it was a rule that could be shown to be true. Al-Khwarizmi goes further still, extending this reasoning into what we would now call algebraic multiplication, showing, entirely in words with no symbols at all, how to multiply expressions of the form a number plus an unknown quantity by another expression of the same kind, working out the resulting terms one by one. To a modern eye trained on symbolic shorthand, watching someone reason through a plus bx c plus dx using nothing but sentences can look almost painfully slow. But the historian Roshdi Rashed has argued that there is real conceptual depth hiding inside that apparent simplicity. That Al-Khwarizmi's treatment of equations with a single unknown, worked out through this careful, deliberate arithmetic of related expressions, represents something genuinely new. Algebra conceived as a general theory of equations, not just a bag of isolated tricks for isolated problems. After presenting the 6 equation types and their solutions, Al-Khwarizmi's book moves into pages of worked applications, practical problems involving land, geometry, and trade, and then, in its final major section, into a lengthy and technically demanding discussion of Islamic inheritance law, showing how the linear equations from earlier in the book could be used to calculate the precise shares owed to different heirs under Islamic legal rules. It is, in many ways, less a pure mathematics book by modern standards and more something closer to a professional manual, the kind of text a judge, a merchant, or a land surveyor in 9th century Baghdad might actually keep close at hand. Chapter 5. The Father of Algebra. Al-Khwarizmi is very often introduced with a title, The Father of Algebra. It's worth stopping to ask what that title actually means and whether it's fair. He was not the first person in history to solve equations. Babylonian mathematicians, more than 1,000 years earlier, had methods for solving certain kinds of quadratic problems, even though they expressed them very differently. The Greek mathematician Diophantus, writing centuries before Al-Khwarizmi, worked extensively with what we'd now recognize as algebraic problems, though his approach and notation were quite different and were focused more narrowly on number theory. Indian mathematicians had also developed sophisticated methods for handling unknowns and equations well before Al-Khwarizmi's time. So what then earns him the title? The historian Solomon Gans, writing about this exact question, argued that Al-Khwarizmi has a real claim to being called the father of algebra, in some respects a stronger claim than even Diophantus, but precisely because he was the first to teach algebra as its own independent subject, taught for its own sake, and organized around a general systematic method, rather than as a tool folded into number theory or embedded in scattered individual problems. That is the real distinction this documentary wants to hold on to. Al-Khwarizmi did not invent the idea of an unknown quantity, and he did not invent every technique in his book from nothing. What he did was take existing mathematical knowledge from Greek geometry, from earlier Near Eastern traditions, from the broader intellectual currents flowing through Baghdad, and organize it into the first known text devoted specifically and systematically to algebra as its own discipline, with a general method that could, in principle, be applied to any equation of the type he described. It's not a small thing. Even historians who are otherwise cautious about overstating his originality, and some are quite cautious. The classicist G.J. Toomer himself, in an assessment quoted by other historians, judged Al-Khwarizmi's overall scientific achievements rather modestly, still recognized that the systematic, teachable general nature of his algebra treatise was something new. Other historians, like Roshdi Rashid, take a much stronger view, describing the originality of Al-Khwarizmi's conception and style as difficult to overstate. The truth, as is often the case in the history of ideas, probably sits somewhere between those two assessments, and reasonable historians disagree about exactly where. The historian of science George Sarton, in an assessment quoted by later scholars, went further still, describing Al-Khwarizmi as one of the greatest mathematicians of his time, and, taking the surrounding circumstances into account, among the greatest of any time. Not every historian would put it quite that strongly. But even setting the boldest praise aside, what's clear is that father of algebra is less a claim about pure invention and more a claim about a moment, the moment when the scattered techniques for handling unknown quantities were gathered into a single, organized, generalizable discipline with a name of its own. The comparison with Diophantus is worth drawing out a little further because it captures the distinction precisely. Diophantus, writing in Alexandria several centuries earlier, worked through a long series of specific numerical problems, each solved with a clever, often problem-specific trick, and his work sits within the broader field of number theory. Al-Khwarizmi's approach runs in almost the opposite direction. Rather than a collection of clever one-off solutions, he built a small number of general categories, the 6 standard equation types, each with a repeatable method that could, in principle, be applied to any equation of that shape, regardless of the specific numbers involved. That shift from solving problems to building a method is really the crux of why so many historians reach for the word father when they describe him, even while disagreeing about how original any single piece of his mathematics actually was. Chapter 6. The words themselves. It's worth lingering just for a moment on the 2 Arabic words at the center of all this, al-Jabr and al-Muqabala. Al-Jabr carries a sense of restoration or completion, putting something broken back together, or, in the mathematical sense Al-Khwarizmi used it, restoring a missing or negative quantity by adding it back to both sides of an equation until nothing is left subtracted. Al-Muqabala means something closer to confrontation or balancing, setting 2 things opposite each other and cancelling out what matches. When Latin translators, working centuries later in medieval Europe, rendered the title of Al-Khwarizmi's book into Latin, the word Al-Jabr was carried over almost untouched, becoming algebra. The mathematical operation had become the name of the entire field. Here is the strange and quiet thing worth sitting with. Every time a student anywhere in the world today writes the word algebra at the top of a worksheet, they are, without any awareness of it, saying an Arabic word from a 9th century Baghdad manuscript, a word that originally just meant putting something back together. Chapter 7, from Al-Khwarizmi to algorithm. There is a second word hiding inside this story, and it may be the more surprising of the two: algorithm. Al-Khwarizmi also wrote a separate treatise on arithmetic, specifically on how to calculate using the Hindu-Arabic numeral system. The original Arabic text of this work has been lost. What survives is a Latin translation known by the title Algoritmi de Numero Indorum, roughly Al-Khwarizmi on the Hindu art of reckoning. Historians note that this Latin version is known to differ in various ways from whatever Al-Khwarizmi originally wrote, and that even the original title of his Arabic text is no longer known with certainty. But the Latinized form of his name in that title, Tughi Algoritmi, is the direct ancestor of the word we use today. Here's how the chain worked, as best historians can reconstruct it. In Latin, Al-Khwarizmi's name became algoritmi. Over the following centuries, as European scholars used this word to refer to the step-by-step methods of calculation his arithmetic treatise had taught, it slowly drifted away from being a proper name at all and turned into an ordinary noun, first as algorithm, referring specifically to the process of calculating using Hindu-Arabic numerals, and eventually, through further linguistic drift over the following centuries, into the broader modern word algorithm, meaning any well-defined step-by-step procedure for solving a problem. It is important to be precise about what this does and doesn't mean. Al-Khwarizmi did not invent the concept of a step-by-step mathematical procedure. Such procedures existed in Babylonian, Greek, and Indian mathematics long before him, and he certainly did not invent anything resembling a modern computer algorithm. He lived and worked more than 1,000 years before anything like a computer existed. What happened is something more specific and in its own way more remarkable. His name, carried through the accident of a translated book title, became permanently attached to the very idea of a systematic calculating procedure, so permanently that the word describing that idea today no longer even sounds like a name. Think about what that means for the modern world. Every time a piece of software runs at some level an algorithm, every recommendation a streaming service makes, every route a mapping app calculates, every search result ranked and returned, every process that sorts, filters, predicts, or calculates behind the screen of a phone or a laptop, all of it is described in the language of computer science using a word that is at its root a distorted echo of one 9th century Baghdad scholar's name. He could not have imagined any of this. The scale, the speed, the sheer ubiquity of algorithmic processes in 21st century life would have been unimaginable to someone writing arithmetic instructions by hand for merchants and surveyors in Abbasid Baghdad. But the thread connecting his name to that modern reality, however thin and however indirect, is real. It survived translation into Latin, survived the fall and rise of different intellectual centers across 1,000 years, survived the transition from handwritten manuscript to printed book to digital text. And it is still there, quietly, every time someone uses the word. After Al-Khwarizmi. Before moving on from mathematics to the rest of Al-Khwarizmi's work, it's worth briefly noting what happened to his algebra after he set it down. His treatise did not sit unread. Later mathematicians working in the Islamic world took his 6 standard equation types and extended them. The Egyptian mathematician Abu Kamil, writing roughly a generation or two after Al-Khwarizmi, built directly on his methods, working with more complicated equations and irrational quantities, and his own work would later influence Fibonacci in Europe. Other mathematicians across the following centuries, in Baghdad, in Cairo, in Muslim Spain and elsewhere, continued refining algebraic method, gradually extending it toward cubic equations and beyond, well past anything Al-Khwarizmi himself had attempted. This matters because it's a useful corrective to any version of this story that treats Al-Khwarizmi as a lone, final word on algebra. He wasn't an ending. He was closer to a beginning. The author of the first systematic textbook in a field that other mathematicians across several more centuries and several more regions would continue to build outward from long before any of it reached Latin-speaking Europe at all. If this kind of story is one you'd like to keep returning to, histories of the scholars, inventors and thinkers whose names have quietly folded themselves into the language of everyday life, Sleep with Islam exists for exactly that. There's no rush here, and nothing more you need to do right now except keep listening. Let's go back to Baghdad and to the rest of what Al-Khwarizmi built. Chapter 8. Numbers, Zero, and the System We Still Use. Al-Khwarizmi's arithmetic treatise, the one whose Latin title gave us algorithm, dealt with something that sounds almost too basic to matter and turns out to matter enormously: how to calculate using the numeral system with the 10 digits, 1 through 9 plus 0, arranged by position. This numeral system did not originate with Al-Khwarizmi, and the documentary wants to be very clear about that. The system had Indian origins, developed over an earlier period by Indian mathematicians and astronomers. What Al-Khwarizmi's arithmetic treatise did was describe and systematically explain how to calculate using this Hindu place-value system, explaining the role of each of the 9 digits and the crucial role of 0 as a placeholder that lets position itself carry mathematical meaning. According to historians who have studied the surviving Latin translation closely, the first known systematic use of 0 as a placeholder in positional notation may be found precisely in this work of Al-Khwarizmi's, not the invention of 0 itself, which has its own separate and much older history rooted in Indian mathematics, but its first thorough, systematic explanation for a new audience. Why does that matter so much? Because positional notation, the simple fact that the digit 5 means something different depending on whether it sits in the ones place, the tens place, or the hundreds place, is what makes modern arithmetic fast. Try for a moment to imagine multiplying 2 large numbers using Roman numerals. There's no clean, repeatable procedure. Every calculation becomes its own small puzzle. Positional notation replaced that with a small set of repeatable rules that work the same way every time, for numbers of any size. That shift from ad hoc calculation to systematic, repeatable procedure is, in its own quiet way, one of the ancestors of what we'd now call algorithmic thinking. Al-Khwarizmi's arithmetic treatise helped carry this Indian numeral system into the Arabic-speaking scholarly world, and later, through Latin translation, into medieval Europe, where it would gradually, over centuries, and against real resistance from those attached to older counting methods, replace Roman numerals in everyday commercial and scientific use. 7 separate 12th century Latin treatises, historians note, drew directly on this lost Arabic original, each one a small link in the chain carrying the system westward. It's worth returning to the point this documentary keeps circling back to. Al-Khwarizmi did not invent the digits, and he did not invent 0. Zero's own history runs deeper and further back than Al-Khwarizmi's lifetime. Indian mathematicians and astronomers had already been developing the concept of 0 as both a placeholder and, gradually, as a number in its own right for a considerable time before his work. What Al-Khwarizmi did was take an existing, powerful idea, understand it with enough depth to explain it clearly to others, and put it into a form that could travel. Sometimes that is the harder and more historically consequential achievement, not the spark of invention itself, but the patient work of making an idea usable, teachable, and transportable across a civilization, and eventually across the world. There's a genuinely interesting lesson tucked inside this part of the story, one worth pulling out explicitly. A civilization does not have to invent an idea from nothing in order to change the course of history with it. Sometimes the more consequential contribution is what happens after the original spark, the work of understanding an idea deeply enough to explain it clearly, organizing it into a form that a student or a merchant could actually use, and carrying it somewhere it hadn't been before. India gave the world positional numerals and the concept of zero. Al-Khwarizmi's arithmetic treatise gave the Arabic-speaking world, and eventually medieval Europe, a systematic explanation of how to actually calculate with them. Both steps mattered. Neither would have had nearly the same impact alone. Chapter 9. The Sky Above Baghdad. Algebra was not the only field Al-Khwarizmi worked in. He was also, by profession and by patronage, an astronomer. His major astronomical work is known as the Sindind Zai, an astronomical handbook built, as its name suggests, on an Indian astronomical text. According to the historical record, that Indian text had arrived in Baghdad decades earlier, around 770, brought as part of a diplomatic gift from an Indian delegation to the Abbasid court. Al-Khwarizmi's version of this material set him apart in one interesting respect. While most later Islamic astronomical handbooks were built on the Greek planetary models found in Ptolemy's Almagest, Al-Khwarizmi's Zij was based instead primarily on Indian astronomical methods. Even though historians believe he was likely also familiar with Ptolemaic material circulating through translations already available to scholars in Baghdad. The original Arabic versions of this astronomical work, there appear to have been two, an earlier and a later version, have both been lost. What survives are Latin versions, a 10th century critical revision made by the astronomer Al-Madriti, later translated into Latin by Adelard of Bath, along with a separate Latin version of the longer original. Between them, these surviving texts cover a substantial range of astronomical topics: calendars, the calculation of the true positions of the sun, moon, and planets, tables of trigonometric values, spherical astronomy, tables used for astrological purposes, and calculations relating to eclipses and to the visibility of the new moon. A calculation with real religious significance, given its role in marking the start of the Islamic lunar month. This is worth pausing on because it's a useful reminder that astronomy in this period was never purely theoretical stargazing. It had direct practical stakes, determining prayer times, marking the beginning and end of the fasting month of Ramadan, calculating the direction of prayer, building calendars that a growing administrative empire could actually run on. Al-Khwarizmi's astronomical tables sat at the intersection of mathematics, religious practice, and the day-to-day machinery of a large state. Picture, for a moment, an astronomer in this period working through the night, not with a telescope, which wouldn't exist for several more centuries, but with instruments like the astrolabe, tracking the visible positions of stars and planets against carefully calculated tables, checking observation against calculation, correcting small errors inherited from an older source, adjusting figures for Baghdad's own latitude rather than the latitude of wherever the original data had first been recorded. It was slow, exacting work, with real consequences if it went wrong. A miscalculated new moon could shift the start of a religious observance for an entire community. Once again, the honest, historical picture resists a simple story of singular genius. Al-Khwarizmi was working with numerical values drawn substantially from Indian astronomers within a broader tradition that was also, in various indirect ways, in dialogue with Ptolemaic Greek astronomy. His contribution was not the invention of astronomy from nothing, but the careful adaptation, calculation, and systematic presentation of these traditions for use in the Islamic world of his time. There's a small, almost poignant detail buried in the surviving scholarship on Al-Khwarizmi's astronomical tables. A separate manuscript on spherical trigonometry has also been attributed to him, dealing with the mathematics needed to calculate positions and angles on the curved surface of the celestial sphere, the same kind of geometry that centuries later would underpin navigation, cartography, and eventually satellite positioning. Whether every detail of that attribution is fully secure is a question specialists continue to examine, but it fits the broader shape of a scholar whose mathematics moved fluidly between pure calculation, geometry, and the practical needs of timekeeping and observation. Chapter 10. Mapping the Earth. Al-Khwarizmi also produced a major work of geography, generally known by the title Kitab Surat al-Ard, the book of the description of the Earth, or, as it's sometimes rendered, the image of the Earth. This was an ambitious undertaking. According to historians who have examined the surviving manuscripts, the work provides latitude and longitude coordinates for over 2,400 locations, intended as the basis for constructing a world map, cities, mountains, seas, islands, geographical regions, and rivers, all listed with their coordinates. The book was based in large part on the geography of Ptolemy, the Greek astronomer and geographer, whose work had already become a foundational text for this kind of project. And this is the interesting part. Al-Khwarizmi's version was not simply a copy. According to historians, the maps that accompany his manuscript are, on the whole, more accurate than Ptolemy's original. Where Al-Khwarizmi had access to better local knowledge, particularly for the regions of the Islamic world, Africa, and parts of the Far East, his data noticeably improves on Ptolemy's older figures. For Europe, by contrast, where Al-Khwarizmi had less independent access to updated information, his work appears to rely more directly on Ptolemy's original data, uncorrected. That pattern tells a clear story on its own. Muslim scholars in this period were not simply preserving ancient Greek knowledge in amber. Where they had better access to the world through trade routes, travel, administrative records, and direct contact with regions Ptolemy himself had only known second-hand, they revised and improved it. Geography, like algebra and astronomy, moved forward here rather than staying frozen in place. It's worth imagining for a moment the sheer labor behind a project like this. 2,400 locations, each requiring a coordinate pair, gathered from travelers' reports, administrative records, older geographical texts, and astronomical calculation, then cross-checked, corrected, and organized into a single, coherent reference work. All of it done by hand, without satellites, without any of the surveying instruments that would come centuries later. It's the kind of enormous, patient, unglamorous labor that rarely survives in popular memory the way a single dramatic discovery does, but that quietly built the infrastructure later scholars, travelers, and mapmakers would depend on. Chapter 11. Mathematics as a tool for ordinary life. It's easy once you start talking about equations and astronomical tables to lose sight of why any of this mattered to the people actually living in 9th century Baghdad. So it's worth returning briefly to the ground-level problems Al-Khwarizmi's algebra was built to solve. How much land does this plot actually contain? How should a family's inheritance be divided fairly according to the detailed proportional rules of Islamic law? How much material is needed to complete a building project? How can a merchant calculate a fair price across a complicated trade? These were not abstract puzzles. They were the daily friction points of an enormous, wealthy, rapidly administered empire. And Al-Khwarizmi's algebra treatise devotes a substantial portion of its length to exactly these kinds of worked, practical examples, most notably the detailed inheritance calculations that make up its final section. This is, in a way, the most human part of the story. Algebra did not begin its life as an abstract subject taught for its own intellectual beauty, tucked away from the concerns of ordinary people. It began in Al-Khwarizmi's hands as a working tool, a way of turning a real dispute over land or property into a clear, solvable question with a definite answer. The elegance came later. The urgency came first. The inheritance section of his algebra treatise deserves a little more attention than it usually gets, because it is, in some ways, the most demanding part of the whole book. Islamic inheritance law assigns specific, carefully defined, fractional shares to different categories of relatives. A surviving spouse, children, parents, siblings, with the exact shares shifting depending on which combination of relatives happens to survive the deceased. Working out those shares correctly, especially in complicated family situations with several categories of heirs entitled to different fractions of an estate, could require real mathematical care to avoid errors that might otherwise take a fraction larger than what was legally due, or smaller. Al-Khwarizmi's treatise walks through case after case of this kind, using the same equation-solving methods introduced earlier in the book, adapted to the specific legal fractions involved. It is not, admittedly, the most thrilling reading by modern standards, but it is a vivid, detailed record of mathematics being put directly into the service of fairness, case by case, family by family. Chapter 12. How Knowledge Crosses Borders. By now a pattern should be visible, and it's worth naming directly. Almost nothing in this story moved in only one direction. Indian mathematicians developed the positional numeral system and the systematic use of zero. Al-Khwarizmi explained and organized this system for a new audience in Arabic. Indian astronomers built the tables underlying the Sindinzi. Al-Khwarizmi adapted and systematized them, likely alongside some awareness of Greek astronomical traditions arriving through translation. Greek geometry, whether directly through Euclid or indirectly through broader regional traditions, shaped the reasoning behind his algebraic proofs. Ptolemy's geography gave him a starting framework that he and other scholars in Baghdad then corrected and improved with newer, more local knowledge. None of this was a simple, tidy relay race, a baton passed cleanly from India to the Islamic world to Europe, each civilization doing its part and stepping aside. It was messier and more interesting than that. Translation, cross-checking, disagreement, correction, synthesis, and reteaching carried out over generations by scholars who didn't always agree with each other, working in a city that had made a deliberate institutional effort through royal patronage, a major library, and a program of translation, to gather mathematical and scientific traditions from multiple civilizations into conversation with one another. Al-Khwarizmi sits at one particularly important junction in that much longer chain. He was neither the first link nor the last. But the specific books he wrote, the algebra treatise, the arithmetic treatise, the astronomical tables, the geography, happened to become unusually influential links, ones that a later chain of translators would carry directly into medieval Europe. It's worth noticing, too, how much of this chain depended on institutions rather than individual brilliance alone. A single gifted mathematician working in isolation leaves far less of a mark than a mathematician working inside a city that has deliberately built a library, funded translators, and gathered a critical mass of other scholars working on related problems. Al-Mamun's investment in the House of Wisdom, in observatories, and in a sustained program of translation created exactly the kind of institutional soil in which a figure like Al-Khwarizmi could do work that traveled. Ideas rarely move across centuries and civilizations on the strength of one person's talent alone. They move because someone, often a ruler or a patron with resources far beyond any single scholar's own, builds the institutions that let ideas be written down, copied, stored, and eventually rediscovered by someone in a different country, speaking a different language generations later. Chapter 13. Europe meets Al-Khwarizmi. That next link in the chain came several centuries later, through the medieval European tradition of translating Arabic scientific and mathematical texts into Latin. Al-Khwarizmi's Algebra treatise was translated into Latin more than once, notably by the English scholar Robert of Chester in the 12th century, and separately by the Italian scholar Gerard of Cremona. His arithmetic treatise survives, as already discussed, only through its Latin translation, under the title that gave English the word algorism, and eventually algorithm. His astronomical tables reached Europe through Adelard of Bath's Latin translation of Al-Majriti's revised version. Through these translations, Al-Khwarizmi's name and the title of his most famous book entered the vocabulary of European mathematics directly. Algebra became algebra. The Latinized form of his own name, Al-Khwarizmi, slowly reshaped itself over the following centuries into algorithm and then algorithm. European mathematicians who studied these Latin texts, figures like Leonardo of Pisa, better known as Fibonacci, who helped popularize Hindu-Arabic numerals in Europe through his own writings in the early 13th century, were in a very direct sense building on foundations Al-Khwarizmi's work had helped lay 400 years earlier. Fibonacci's own path into this story is worth a brief mention. As a young man, he traveled with his merchant father to North Africa, where he was introduced to the Hindu-Arabic numeral system and the arithmetic methods built around it, methods that, by this point, had been circulating through Arabic mathematical and commercial culture for centuries, carrying forward the systematic explanation Al-Khwarizmi's arithmetic treatise had helped establish. Fibonacci returned to Italy and in 1202 published a book called Liber Abaci, the Book of Calculation, arguing for the enormous practical advantages of this positional numeral system over the Roman numerals still dominant across most of Europe at the time. It would still take a couple more centuries before Hindu-Arabic numerals fully displaced Roman numerals in everyday European commercial life, but Fibonacci's book is generally recognized by historians as one of the most important single steps in that long transition. A transition that traces back, link by link, through Arabic mathematical culture to the same numeral system Al-Khwarizmi had explained centuries before. It would be a mistake, and a needlessly combative one, to frame this as a story of one civilization simply taking from another. The more accurate framing, and the one this documentary wants to sit with, is that knowledge crossed a linguistic and cultural border because scholars on the receiving end recognized its value and made the deliberate, difficult effort of translation. That is, in the end, how civilization actually advances, not through any single culture inventing everything in isolation, but through ideas being picked up, understood, translated, and carried somewhere new by people willing to do the patient work of crossing that border. Chapter 14. What we actually know. It's worth returning one more time to something raised earlier, because it deserves to be sat with rather than rushed past. We know in real and traceable detail what Al-Khwarizmi wrote. We know the structure of his algebra treatise, its worked examples, its geometric proofs. We know the outline of his astronomical tables and the scope of his geographical coordinates. We can trace, book by translated book, how his work moved outward across centuries and languages, and we can see its fingerprints in the mathematics still taught today. But about the man himself, his temperament, his private life, his relationships, the small details that make a historical figure feel like a person rather than a name on a manuscript, remarkably little survives. Historians who specialize in this period are explicit about how thin the record is, and explicit in warning against the temptation to fill that thinness with invented detail dressed up as fact. There is something quietly moving in that. The work outlived the man almost completely. What remains is not a portrait, not a diary, not even a firm agreement among historians about exactly where he was born. What remains is a handful of books copied, translated, argued over, and carried forward by hands that were not his own, and that in the end turned out to be enough to change how a large part of the world calculates. Chapter 15. Scholarship and the Muslim Were. world. It's worth stepping back, briefly, to place Al-Khwarizmi's story inside a slightly wider frame. This documentary is not making the claim that science or mathematics began with Islam, or that the Muslim world alone was responsible for the mathematical knowledge of this period. That would flatten a much more complicated and much more interesting truth. What can be said fairly is that the intellectual culture of Abbasid Baghdad, particularly under caliphs like Al-Mamun, placed real institutional value on learning, funding translation, building libraries, supporting astronomers and mathematicians, and drawing scholars from a genuinely diverse range of backgrounds and traditions into a shared conversation. Within that environment, there is also a long-standing Islamic intellectual tradition that frames the pursuit of beneficial knowledge as something worth honoring in its own right, not as an add-on to religious life, but as connected to it. Scholars like Al-Khwarizmi worked within and were supported by a civilization that had, for a period, made the deliberate choice to invest heavily in learning, translation, and scholarship as part of its own self-understanding. That's a real and meaningful historical fact, worth stating plainly, without needing to inflate it into something grander than it was. It's also worth noting that this same intellectual culture extended well beyond mathematics. In the decades around and after Al-Khwarizmi's lifetime, Baghdad and other centers of the Islamic world supported major advances in medicine, optics, chemistry, philosophy, and astronomy, carried forward by scholars working in a similar spirit, translating, testing, correcting, and building on earlier traditions rather than treating them as fixed and untouchable. Al-Khwarizmi's Algebra treatise is simply one especially well-documented and especially consequential example of a much broader pattern of scholarly activity that characterized this period of Islamic intellectual history. Chapter 16. Why this story is worth knowing. You don't need to understand quadratic equations to get something out of Al-Khwarizmi's story. You don't need to be a mathematician or even particularly interested in math to find something worth carrying from it. What he represents is something a little broader than any single equation, a tradition of intellectual curiosity, patience, and care. The willingness to take a difficult, half-formed body of knowledge and do the slow work of organizing it, explaining it clearly, and passing it on in a form that could survive translation into other languages and other centuries. That is worth remembering not as a point of pride to be defended, but as a point of connection, a reminder that Muslim scholars in this particular period and place participated meaningfully in building the shared body of knowledge that the whole world now draws on, alongside contributions from many other civilizations before and after them. Knowing this history isn't about claiming exclusive ownership of algebra or of algorithms. It's about understanding, honestly, what came before us, and, in turn, asking a quieter question about what we ourselves might be leaving behind for the people who come after. Chapter 17. Al-Khwarizmi in the Age of Artificial Intelligence. Here is where the thread we've been following all night finally reaches the present. Al-Khwarizmi's name, transformed by Latin translation into algorithm, now describes something at the very center of modern computing. Every piece of software runs on algorithms, precise step-by-step procedures for solving a defined problem. Every search engine ranks its results with algorithms. Every recommendation system, every navigation app calculating a route, every piece of financial software processing a transaction, every large-scale artificial intelligence system performing the enormous chains of mathematical operations that let it generate language or recognize an image, all of it, at some foundational level, is built from algorithms. He did not create any of this, and it would badly misrepresent his story to suggest otherwise. He lived and worked more than 1100 years before anything resembling a computer existed. What connects him to this modern world isn't direct invention. It's the much longer, quieter thread of procedural, systematic mathematical thinking. The idea that a problem could be approached not through guesswork, but through a repeatable, teachable method. A thread his own work helped strengthen and carry forward, centuries before anyone could have imagined where it would eventually lead. So here is the strange fact worth sitting with as this chapter closes. When a piece of software somewhere quietly decides what appears on a screen, when an AI system performs a vast chain of calculations to generate a response, the word used to describe that entire process is, at its root, a distorted echo of the name of a mathematician working by hand in 9th century Baghdad, dividing inheritances and measuring fields. He could not have imagined the scale of what his name would eventually be attached to. But the thread is real, and it is still there. There's a useful humility in sitting with that gap, honestly. It would be easy, in a documentary like this one, to slide from his name is linguistically connected to the word algorithm into something much bolder and much less accurate. He invented modern computing, or he predicted artificial intelligence. Neither of those claims is true, and neither is necessary. The actual truth is quieter and, in its own way, more interesting. An idea about systematic step-by-step calculation, carefully written down and explained by one scholar in one city, proved durable enough to survive translation, survive centuries of political and technological change, and end up lending its name, almost by accident, to one of the defining concepts of an age its original author could never have foreseen. That kind of long-delayed, indirect influence is, if anything, a more remarkable story than a tidy myth of direct invention would be. Chapter 18. 2 words, 1 legacy. Let's gather the 2 threads of this story back together. Algebra, from Al-Jabr, completion or restoration, one half of the method Al-Khwarizmi used to solve equations, taken from the title of his most famous book. Algorithm, from Algoritmi, the Latinized form of his own name, attached to his treatise on Hindu-Arabic arithmetic, and slowly reshaped by centuries of language into the word we use for any systematic calculating procedure. 2 words. 1. Scholar. A life we know almost nothing about, and a body of work that quietly reorganized how enormous parts of the world calculate, measure, and eventually compute. They are no longer just abstract terms after tonight, hopefully. They carry a manuscript behind them, a city on the Tigris, a caliph's patronage, a house of wisdom filled with translators, a slow, uneven, centuries-long journey across languages and borders, and at the far end of that journey, the modern world, search engines, navigation apps, artificial intelligence, and a phone in your pocket, all quietly carrying forward a name from 9th century Baghdad. Let's go back to where we started. X plus 5 equals 12. At the beginning of tonight's story, it looked ordinary, almost too plain to notice. Now, hopefully it carries something more, the quiet weight of a word with a 1,000-year history behind it, a word that traces back through Latin translators, through Baghdad's house of wisdom, to a scholar whose name we barely know beyond the books he left behind. Think back for a moment over everything that had to happen for that small line of symbols to exist on a page in front of you or in front of a student anywhere in the world this evening. A caliph in 9th century Baghdad had to value learning enough to fund a house of translation. Scholars had to gather from different traditions, Greek, Persian, Indian, and the emerging voice of Arabic mathematics itself, into something like a shared conversation. One mathematician among them had to sit down and do the patient, unglamorous work of organizing scattered techniques into 6 standard cases, each with a provable method. His book had to survive being copied by hand generation after generation, in a world with no printing press. Translators, centuries later and a continent away, had to consider it valuable enough to render into Latin, word by careful word. And European scholars, further centuries on, had to absorb it, teach it, and slowly fold its vocabulary into their own languages until Algebra no longer sounded foreign at all, until it was simply algebra, a word so ordinary that almost no one pauses to ask where it came from. Every single link in that chain could have broken. A library could have burned. A translator could have chosen a different text. The manuscript could have been lost, as so many others from this same period genuinely were. None of it was guaranteed. And yet, somehow, enough of it held together that a scholar's name from 9th century Baghdad is quietly present, right now, in the vocabulary of computer science in classrooms on every continent, in a word most people use dozens of times without a second thought. And the next time you hear the word algorithm in a conversation about a phone app, a recommendation, a piece of software, an AI system, perhaps you'll remember just for a moment that its own history leads back to that same city and that same scholar carried into the modern world through the accident of a Latin book title. The point of remembering Muhammad ibn Musa Al-Khwarizmi was never to claim that every modern invention belongs to a single civilization or that one culture alone built the world we live in now. It's something quieter than that and maybe more useful. Knowledge moves in a long chain. Someone receives an idea. Someone studies it, tests it, understands it more deeply. Someone organizes it and explains it clearly enough that it can be taught. Someone translates it into a language it wasn't born in. Someone carries it somewhere new. And centuries later, someone else, who may never even learn the original names in the chain, builds something entirely new on top of it. That is how human knowledge actually moves. Not in a straight line from one genius to the next, but as a long, uneven relay carried by translators and teachers and copyists as much as by the original thinkers themselves. So perhaps the quieter question worth carrying forward from tonight isn't really about the 9th century at all. It's about now. What might we, in our own small way, be adding to that same long chain? Not necessarily an invention with our name attached to it. Perhaps something smaller. A piece of understanding passed to someone else. A problem solved clearly enough that it helps someone we'll never meet. A small, patient contribution to a body of knowledge none of us will ever see the end of. Al-Khwarizmi almost certainly had no idea, while he was alive, that his name would outlast nearly everything else about him, that 13 centuries later, people in countries that didn't exist yet, speaking languages that hadn't yet formed, would still be quietly carrying a fragment of his identity every time they opened a piece of software or solved for X. He was, as far as the record shows, simply doing careful, patient, occasionally tedious work, organizing equations, checking astronomical tables, correcting a map here and there where better information had come in. There's something worth sitting with in that. The people who end up mattering most across centuries are not always the ones chasing recognition. Sometimes they're simply the ones who did unusually careful, useful work and let it speak for itself long after they were gone. You don't need to remember every detail from tonight. Not the dates, not the 6 standard equation types, not the precise details of the Sindhind Z. If anything stays with you, let it just be 2 words. Algebra. Algorithm. 2 ordinary words sitting quietly inside sentences we use every day. And behind them, a story that began more than 1,000 years ago, in a city that no longer exists in quite the same form, carried forward by a scholar whose books traveled far further than he ever could have imagined. Thank you for spending this quiet part of the night with Sleep with Islam. If this kind of slow journey through the history of the Muslim world is something you'd like to return to, you're welcome to subscribe and join us for the next one. Until then, rest well and keep noticing the small, quiet histories folded into ordinary things. Good night.